So what we have here is a classic physics demonstration. We have something called an Atwood machine. It's a fancy name for something very simple. You have a pulley on top and a string that's attached to a mass, and it's also attached to a mass on the other side. If those two masses are equal, they're in balance, so it really doesn't do anything. Force of gravity is pulling the same on the left as it is on the right, so nothing's happening. You can move this and see what will happen to the velocity, constant acceleration, things like that. Since it's equal forces, it should always be constant acceleration once you let go of it. One, I guess, best way to say the most relevant example of Atwood machine is an elevator. So let me get to the next slide. An elevator is essentially an Atwood machine. What we have here is a pulley on top. One side of the cable is connected to the elevator shaft or cart, not shaft, and the other side is attached to counter masses. Ideally, those two masses are very close in mass, so that the motor on top requires very little power or wattage to kind of move the two. The only time that actually requires a little bit more is if you have a lot of load on it, a lot of passengers, or if you want to make it move really fast. But by having this counterweight, it really makes things easier. An example is Angela's flight in downtown LA. You have two trolleys. One will be going down while the other one's going up. Since they have about the same mass, it requires very little energy to move it up or down. So if you ever played with it, the pulley will change the direction of it, and then we can do it. Now, other than elevators, what's good about it? Well, it's actually a great way to understand how overall acceleration works and how we could calculate tension and what happens to tension in an overall system. So what we have here is my favorite actor. I'm kind of being sarcastic, kind of not being sarcastic. I love Tom Cruise's movies. They're always entertaining. They're a lot of fun to watch, but at the same time, it's always Tom Cruise. Here, let's assume his vertical acceleration is 0. He's not moving up or down. Technically, he's running left and right on the building, but we're just going to focus on his up and down motion. You have force of gravity that's acting on him, pulling him down, Fg, and he's not falling to the ground because he's attached to a rope that is pulling him up. That's kind of too big. About the same amount, or actually exactly the same amount. And I'm going to call this force of tension. There's two ways to write it. Ft is one way. Another way is just having T. I personally prefer Ft, but T is also being seen. So I kind of want to show you both. So here you have, let's say, sum of all forces. In the y direction, you have force of gravity plus force of tension. Since he is not moving up or down, increasing his speed, then a is equal to 0. So if we substitute this, ma is equal to fg plus ft. Since a is equal to 0, the whole entity is 0. So we have 0 equals fg plus ft. If we move fg to the other side, then we have negative fg equals ft. So very similar to how Fn works. So both Ft and Fn, force normal, can only be determined by sum of all forces. Okay. So for Fn, remember it's usually countering force of gravity. And for tension, it's pretty much the same. It is countering force of gravity or another pull that it's going to have. So there is no special equation for force tension. It's not like mg mu Fn. It really is just you have to look for the sum of all forces, calculate that, and find all the other forces acting on it to find Ft. Surprisingly, this was a really hard picture to get. So just to have a kid holding up a fishing line, the fish line goes up to here. Unfortunately, I couldn't find it, and then you have a line coming down. So what I want to show you here is if we look at the entire system, tension cancels out. So before, we just looked at Tom Cruise itself. But if we look at the whole system, an interesting property occurs. So here we have a fish, and you have force of gravity on the fish. The fish is being pulled up by the string or the fishing line. This fishing line is kept taut because there's a fishing pole. So the fishing pole is pulling up. I'm going to call it force applied. And overall, the pole feels like the tension's pulling down. So here we have 4 forces. We have force applied on top, tension, tension, force of gravity. Okay, so we have 4 forces. Let me make sure I get my sign correctly. This one's negative, this one's positive, negative, positive. So positive, negative, positive, negative. So that's what we have. But since there's a positive and a negative here, tension cancels out. So sum of all forces here is equal to force applied plus negative force of gravity. And that kind of makes sense, right? If the fish weighs 10 newtons, then you're pulling up on the fishing pole 10 newtons. What the string it's doing itself is transferring that force from one area to another. So the string itself, or the rope, is pulling in on itself, same but opposite direction. So if it is pulling down here at 10 newtons, it's going to pull up here 10 newtons, etc. So these two T's are going to be equal but opposite. If we look at the whole system, they cancel out. Now, let's actually try to find some answers here. If mass of the fish is 2 kilograms, and let's say acceleration is 0, the kid's just holding it still, I want to find tension. Well, how would I do that? I can't use this one. And the reason is because tension cancels out, so no matter how I kind of plug everything in, T's always cancel out, so it's not going to work. So as a whole system itself, it's not going to work. So what we're going to do is just focus on the fish only. So here's my fish. It has a mass of 2 kilograms. So 2 times 9.8 is about, if I could do this in my head, negative 19.6 newtons. If A is equal to 0, I already mentally know that means tension is equal to positive 19.6 newtons. Well, but I'm going to show you the math. Sum of all forces is equal to tension plus force of gravity. And there's only 2 forces because we're ignoring this part because we're just focusing on the fish. Because we are, sum of forces is MA equals T plus MG. And then I'm going to have MA minus MG equals T. And we just plug everything in. In this case, 2 times 0 minus 2 times 9.8 equals tension. Oop. Let me make sure I got that right. Minus, okay. Now, force of gravity, technically is force of gravity, and I left the positive, is negative, so it technically becomes positive. So 2 times 9.8 gives you 19.6 newtons. Okay, so that's kind of how you do it here. So unfortunately, you can't use the whole system, but you could find T. Let's see another example where, in this case, A is not equal to 0. So what I have here is a giant crane pulling up a big bucket of concrete. Let's say the concrete has a mass of 1,000 kilograms. Sorry, I can't display it. How will we find tension if A is equal to 2? So same thing. We're just going to look at it. Okay. Don't worry about the crane, but we're just focused on that bucket. We have force of gravity that pulls down, force of tension that pulls up. Force of gravity is mass times acceleration, 9.8. So this is 9,800. No, sorry, 9,800. There we go. Newtons. I can't make it equal and opposite ft because A is equal to positive 2. So I'm going to set up the equation. Sum of all forces in the y direction is F of t plus F of g. Ma equals F of t plus mg. Technically is negative. I don't want to forget it this time. 1,000 times 2 ft plus 1,000 times 9.8. 2,000 equals ft minus 9,800. If I move this to the other side, I have to add 9,800 each, and then you get 11,800 newtons for force tension. Now, what I like to do always is to mentally check if this is correct. Acceleration is positive up, so that means my force of tension needs to be bigger than my force of gravity. If it's smaller, then negative acceleration will be negative. But since it's positive, force of tension is bigger. This is 11,800, while gravity is 9,800, so it is bigger. So I did my signs correctly. Now, just kind of as a caveat, you can watch A River Runs Through It with Brad Pitt. One of my dreams or bucket lists is to fly fish in somewhere beautiful. And if you've ever seen anybody fly fish, it's actually kind of complex. You're trying to land the fly way off in the distance and tricking the fish that's not attached to anything. Because it's not attached to anything, this part is very thin, almost invisible. But if it's the whole string is very thin, it's very hard to do that casting. So watch the video, you'll understand what I mean by casting. But if it's too light, you can't do that flinging action as it goes back and forth. So you have a fly line that is much, much heavier. Unfortunately, when it being heavier, it's going to be thicker. So you have two different properties of string here. One that's thicker and heavier, and one that's thinner and lighter. Well, why is that significant? Well, if we look at fishing lines, they have different properties, which are right here, how much load they can have. Most of the time in fishing line, they're going to tell you pounds, what it's rated for. So that means it's good to up to 150 pounds, and then there's a high chance of it breaking because of that. Here you have 10 pounds, but yet anything beyond that, you have a good chance of breaking. You might think, well, isn't it better to always just have 150? Well, it might be more expensive. At the same time, it might be harder to catch fish because it's going to be thicker string, more visible, or it might not be as flexible. So it's kind of a balance of two, what kind of things you want. The same thing could be said of a climber's gear. So you want to make sure that you have it rated correctly. So here you can see it's 8.5 kilonewtons is what it's rated for. Anything beyond that, you're risking damaging the nylon or the rope itself. Okay. All right. Now, that's enough tension. Let's get back to Atwood Machine. So here's the classic one where you have a pulley and then two masses. The first one, I'm going to make it pretty simple and redundant. I'm going to make them both the same mass. So 10 kilograms, 10 kilograms. Now, visually, you should see that if they're both the same mass, this thing should not be moving if it's at rest. And even if I move with my fingers, once I stop touching it, it really should stop again. Now, if it was completely frictionless, it will continue to move. But we know that in reality, there is some friction, so it should stop wherever we kind of manipulate it to. So if I put one weight right here, the other one will be down here. And as long as I keep it at rest, it's going to stay that way. But I want to show you the math behind it anyway. So when you have this, you're going to have a bunch of different forces. If we focus on block A, it has force of gravity down. And in order to keep it from moving or falling to the ground, you have force of tension. On B, you have the exactly same thing. You have force of gravity and then force of tension back up. Now, this tension is technically the same, but it's kind of weird because they're both pulling down. But you have to remember pulleys change direction of force. So what we want to do in this case is kind of make our lives easier. Technically, this tension and this tension are against each other. This gravity and this gravity are against each other, but they're in the same direction. In this case, they're working. So you have to remember they're pulling in the opposite direction. To make my signs more correctly, what I'm going to do is I'm going to do a direction of motion. Or DOM for short. And even though you could be wrong, let's say you see a problem, you think, okay, it's going to go to the right or it's going to the left. Even if you're wrong, your answer is still going to be right as long as you get your signs consistent between them. So let me kind of show you. So the direction of motion is going to tell us the sign of my force. If it's in the same direction as the arrow, it's going to be a positive. Same direction, positive. If it's in the opposite direction, it's going to be a negative. In this case, on this side, it is down. So FT is in the opposite direction. FG is in the same direction. Okay. Now, I forgot to say what the purpose of. We want to find A, and we also want to find tension. Okay. For A, we're going to look at the whole system. And I'll hopefully show you in a bit why this is the way you want to do it. So sum of all forces is equal to negative FG, and I'm going to call it A, so I don't get these confused, FGA plus F of T minus F of T plus force of gravity B. Now what's nice is when we look at the whole system, the tensions cancel out. So we're getting rid of an unknown without knowing any of them. So if I substitute all of these back into their formulas, sum of all forces is equal to MA. FGA is negative mass times, mass of A times gravity, 9.8, plus mass of B times 9.8. The trickiest part about this is what this mass is. If we're looking at the whole system, this is all masses. So in this case, it is 10 plus 10. So we have 20A equal to mass of A times 9.8, negative 98, plus mass of B times 98, positive 98. And look, 0. So 20A is equal to 0. A is equal to 0 to 20, or just 0. So hopefully I showed you that way. Now what happens if I want to find tension? Well, unfortunately we can't use the whole system. If we do, tension disappears, so we can't solve for it. So we're just going to focus on one block. It doesn't matter which one, and I'm actually going to do both so that you can see that it's going to give you the same answer. Let's say you have block A. We already determined this is 98 newtons. We want to find tension. I know that I just calculated A is equal to 0. So sum of all forces is equal to tension plus force of gravity A. And then you have 0 equal tension plus force of gravity A. Move it to the other side. Negative force of gravity A equals tension. So negative 98 equals T. And there you have it. So this one's kind of redundant, but I wanted to show you because I want to show you that if you're looking for T, you can't use this one because they cancel out. And you're looking for A, you want to use this one first because you don't have enough information to figure it out. If you didn't have A, you didn't know the left side, you'll have two unknowns as well. All right, let's see one last problem where the masses are not equal. So let's say it is 10 and 20 kilograms. So this one we already know is negative. Oh, I don't want to put a negative. It's just negative. It's just 98. So here the force of gravity is 98. 10 times 9.8. Here should be bigger. Here should be 20 times 9.8. So technically it's just double that. So force of gravity here is 196 newtons. So we have two forces there. We have tensions on top. But in this time, our acceleration is not 0. Right? We want to figure it out because one's heavier, one has more mass, so it should go to the right. And we want to see if we're going to be right. So, in all these problems, you want to do direction of motion. Since this has a bigger mass, most likely it's going to go down. As it goes down, it's going to pull the left one up and over. So this will be my direction of motion. Here DOM is down. Here DOM is up. Okay, so that's the key. Remember, I do this for the signs. Opposite direction, negative. Same direction, positive. Opposite direction, negative. Same direction, positive. So sum of all forces is equal to negative 98 plus t minus t plus 196. MA is equal to 98 newtons. It should be correct. Mass, like I said, this is the tricky part. Since we're looking at the whole thing, it's going to be 10 plus 20. So 30A equals 98 newtons. A is equal to 98 divided by 30, which I believe is about 3.26 repeating. Okay. Now what I'm going to try to do now is to find tension. Remember, I can't use this one because the tension will cancel out. So I'm just going to focus on one. So let's say we're going to do the 10 kilogram first. 98 newtons, and then force of tension, or just T. So sum of all forces is equal to T plus force of gravity. Now, before I move on, just remember that we calculated what A is on the whole system. So here we're focusing on this one. So MA is equal to tension plus mg. MA is 10 times that, 3.26 repeating, equals tension minus, since this is going down, mass, which is 20. Shoot, did I do this right? Oh, I'm looking at the wrong one. Which is 10 times gravity, 9.8. And then you solve for it, you get 98. Move it to the other side. So 98 plus 1. See, oh, I got it wrong. I should just use a calculator. I don't have a calculator. So 10 times 3.26 is just 32.6 repeating. I don't know why I'm struggling. 32.6 repeating equals T minus 98 plus 98 on both sides. You get 130.6 repeating equals tension. If I decided to do the same thing but for the other side, 20, it will be the same thing. But you just have to be careful here that your signs are correct. I found acceleration to be positive 3.26, but it is actually positive, but we're determining it's positive because of this right here. So just be careful when you do it that you get your signs correct. Sum of all forces is equal to Fg plus T, making sure our sign's correct. This one's positive, that one's negative. So MA is equal to positive 196 minus T. Mass is 20. Acceleration we found was 32.6 repeating. No, is that right? No. Oh, right here. Sorry. 3.26 repeating equals 196 minus T. Move it over, and you also get about 130.6. Now, the only difference is this one's negative. All right, so hopefully that makes sense. I'm getting tired, so hopefully I didn't ramble on too much in the end. Let me know in class if you have any questions.